Okay, I'm recording this for those who missed the meeting on Thursday, and it was a pretty short. This one's only gonna be like 10 minutes at most. Intro to state machines. All right, a state machine is a sort of logic that takes an action, and we use rising edge detectors by the way for our actions, and looks at the current state of something, and does a corresponding event. The state we're gonna be talking about today, the type of state machines we're gonna be using today are subsystem based state machines, which means it's going to look at the individual state, like the specific state of the subsystem, whatever subsystem you're talking about. So here's what we had before. We had an action that would correlate to an event, pretty much input, output. The input is your action, or the input causes an action, like your rising edge detector, which leads to a change of state, which is your event. For subsystem based state machines, we have our action, like in our input, like before, but we also have to look at the current state of something. In this case, the subsystem you're modifying. And using those two things, we can do a corresponding event or change of state. So I did some math to figure out how many buttons we would need doing it this way, just one button for one state, pretty much, and it would be 19 buttons. So it's not very efficient, especially with as the more complicated your robot is, the more states there are. So doing one button per state is just not the way to do it. So to reduce this, we just have to lower the amount of buttons we need to modify this. Like for example, this one's a really easy one. The claw, it can either be opened or closed. It only has two states. So there's no need for two buttons for this. We could do this with one. But we need to know the current state of the claw, which is where this comes in. Inside of your subsystem, you should create a method to return the current state of the claw. I called it get current state because when the teleop calls on this function, it will get it would get the current state of the claw. So this is what it returns. You'll see how this works when I actually show it. And this is the data type. It's the states of the claw, what it can be, and this is what it will return. So second thing we need to know though is we need to use a switch case. So that way we can have one variable, not one variable, one corresponding one state corresponding to another change of state. Let me show you. It's easier to show. So here we have our rising edge detector. We learned about this on day 3, I think. Yeah, and then here is our state machine. It's the switch case statement. So this switch looks at the current state of the claw. So claw grab.get current state. And it looks at what states it can be. If it's closed, then it's going to set the claw to open. If it's opened, then you'll set the claw to closed. And this is where using this break thing is especially helpful, because if we didn't, this would be a loop. It would go close to open, open to close. So break just essentially just ends this function, ends this switch case statement. Because if not, it would continue and it wouldn't work properly. So yeah, here's your rising edge detector. Inside your rising edge detector, you have your state machine. In this case, the switch case statement. The switch case is going to look at the current state and then see if it's, for example, in this case, if it's closed, then it'll be set to open, and if it's open, it'll be set to close. The change of state that you see here are called events. I already just said this: open to close, close to open. But there are some issues with this logic. We'll see that. But here's a nice way to map it out. You have your input, you have your action, your rising edge detector. Inside your rising edge detector, you have your state machine, which will have different states that it's currently in correspond to different events or states that they will be set to. So open to close, close to open. Now, there's some issues with this. One, cycling. I'll show you how this works, but basically, this works pretty well with like the claw, because one button is like the minimum you can have for this. But when they have more than two states, it gets a little more problematic. You would want a button for cycling forwards and a button for cycling backwards. That way you have to reduce the amount of time you actually spent pressing buttons. Let me show you. Here's what I call a forward cycle. So in this case, it just starts from all the way back to all the way forward and down. So let's just start upwards. Imagine this is the shoulder. The shoulder is facing upwards towards the ceiling, right? In this case, yeah, the arm shoulder. But when I press, let's just say left bumper, let's say this is the forward cycle, and I press left bumper to activate the state machine. So upwards would go to forwards. Now the arm is down forwards. I press left bumper again, and since I'm forwards, I get set to downwards. So I am all the way down, ready to, able to pick pieces up. And if I press left bumper again, it will restart the cycle by sending me all the way back to chamber intake. And then I press left bumper again, and it just continues this loop each time. Left bumper, left bumper, left bumper, left bumper. So again, it's why using the brake within a switch case statement is pretty important, because if not, it would just cycle through this entire thing with one press. But there could be some issues with just having one cycle, one direction cycle, because what if I'm at chamber intake and I want to go to downwards? I would have to press left bumper 1, 2, 3, 4 times. That's not very efficient when I could just reverse the direction and go back and press, let's say, right bumper once. So we would have a backward cycle. This way, at the very minimum, you can only be 2 button presses away from any state at any given time. Forwards to chamber intake, 1, 2, 3, or 1, 2. See, it's faster if I go, in this case, forwards. But still, this would take 2 buttons though, because you'd want a button for forward cycling and 1 button for backward cycling. Even if you only had 3 states, you still would want to reduce the amount of times you have to press a button. So using that logic, any subsystem with two states would be 1 button, and anything with more than 2 states would be 2 buttons. Did the math here, and that would end up being 10 buttons. Also, these in brackets in parentheses here are the number of states that each subsystem here has. So ultimately, this will come down to 10 buttons, which is kind of a lot. Our goal is 4 buttons. Now, pros and cons. Pros: if we have a simple robot with only a couple subsystems, like 2 or 3, then this is really good, because it's easy to control, and especially for kids, and it's more efficient than not having a state machine. But if you have a more complicated robot, you would have way more buttons, and just in general, having to cycle between multiple states, especially like something this big here, is not very efficient. So you don't want to have to press a button too many times like that. And again, too many buttons if you have too many states. Like 10 is too many. So how can we make it more efficient? Well, one thing is we can make a robot-based state machine. I'll talk about that, but first thing is, at the very minimum, using subsystem-based state machines, you need 1 per subsystem at the very minimum, and we have 6 subsystems, not including the drivetrain. So that would be 6 buttons at the minimum, which is still too many. And this is because subsystems, subsystem-based state machines have to know the state of the current subsystem. If we make a robot-based state machine, we don't. A robot-based state machine, like the name implies, will actually look at the state of the robot itself, like the entire robot, not the individual subsystems. Anyways, here's the stuff you want to know. We really talked about this one today, state machine. Everything else here you should have already heard of before from my other meetings. A state, switch case, rising edge detector, which is a type of action, by the way, and actions and events. Remember, actions lead to events. A state machine looks at an action and looks at the current state of something and does a corresponding event. And that's all I have to yap about today. So this one, cycling as a concept, we shouldn't have to do it, but like honestly, I wouldn't be surprised. Fun fact, during competition, when Dev was controlling the claw, That was subsystem based state machines. I didn't use the robot based state machines like I did for everything else. He would actually have to cycle between the states of the claw, which were like vertical, horizontal, diagonal, left, diagonal, right. So, and then he had like some buttons to directly set the state. Like right bumper would set it to horizontal no matter where you are, and then like left bumper would like open and close the claw. So that is all subsystem based state machines. It is completely separate from the robot based state machine. So we had multiple state machines in our competition bot. Anyways, that's all I'm gonna yap about. This is all the stuff. I'll add all these terminologies to the Goda. I haven't actually added some of these yet, so I'll do that. And I guess that's all.